right? So when you just keep dividing things in half, then it makes it really easy to make a scale, but it makes it hard to do any math with it. Nobody likes doing math with fractions. If I ask you to measure, 5 3/8 of an inch plus 6 and 7/16 of an inch, you're all just grown and want to be able to understand where to round, where the uncertainty is in our measurements and in our calculations. I'm going to pull up my slides on here at least, so I can make sure I don't lose track too much of where we're supposed to go. So we try to stick to just decimal scales, right? And decimal scale specifically means that there's 10 equal divisions in between your larger markings. So if we have 1 meter and about a meter, 2 meters, fractional scale will just keep dividing in half, but if we want a decimal scale, it's harder to make. That's not that bad. That's close to a decimal scale. But you see how much variation there is between those markings I put, and you see why making a fractional scale is a lot easier than trying to make this. But this is the best way to measure things. Right, so if we're trying to measure things, anytime we're trying to measure something, we're always going to approach it, and we're going to measure where we are certain of, according to our measuring implement, and then we're going to go one spot past that. So in terms of a decimal scale, let's assume that this was a well-done decimal scale. Make this one big, that's halfway. If we wanted to measure something with this scale, we could be, if we had an object that was, say, that long, and it continues this way, all the way to 0 over here. If we wanted to measure this, we could look at this and say with absolute certainty that it is definitely, everybody in this room would agree, it's between 1 meter and 2 meters.
Yeah.
Nobody's going to argue that, right? There's no uncertainty there. We would even, assuming my markings were accurate, we could even look at this and everybody would probably agree it's between 1.5 and 1.6. Right? No argument there. Those are the numbers we need, 1.5 something. It's somewhere in between 1.5 and 1.6. And that's where it gets a little hazy, because depending on your eyesight, where you're standing, the scale itself, you might look at that and say, well, I think that looks like it's about a tenth or 3/10 of the way. You might say 1.53. Or somebody else might look at it and say, no, I think it's 1.54. This last digit has uncertainty associated with it. And so in the sciences, our procedure for measuring things is you write down all the numbers you're sure of and go one spot past that and estimate one spot past the smallest decimal markings. We can all agree on these first two numbers, and then we go to one spot past that, and that's where we're going to disagree a little bit. And so, but what you can't do is say, well, that looks to me like it's a quarter of the way. So I'm going to say 1.525. Well, that's a quarter as a decimal, right? But you're indicating that you're sure about that too, and that you're guessing on a 5 if you do that. So anytime we measure anything directly, we're always going to go to the spot where you estimate. Everybody can get close on this last one. Numbers are going to be close to each other. And all of these should be the same no matter what. And so always go and anytime you see a measured number written, you should assume that it's plus or minus 1 in that last digit. This digit, the hundredths place here, we could be off by 1 pretty easily, right? Anybody's number could be off by 1 here. So with that in mind, we always assume that the number that's written has uncertainty in the last digit. And this applies to things that are digital as well. Engineers that build and program digital instruments build in this uncertainty. They don't just report out, a million decimal places, even though the math might indicate that they could do that. They stop where the uncertainty starts. So like if you have your Fitbit, it monitors your Fitbit's even still a thing. Yeah. I have one in my drawer. Okay, cool. The one in my drawer hasn't been charged up since COVID started. So if you have a Fitbit that tracks, how far you're walking every day, it's not going to report out all the way to the foot. It won't tell you how many feet you went. It'll report to usually do about the 100th of a mile, because that's where its uncertainty is. It could be off by 0.01 miles, so it won't report any numbers past that. And so that's what we do in lab as well. You keep very, very close attention to how many decimals you write down when you measure something, because you're telling whoever reads your paper, this is where I'm not sure. Right? And so you do write the one that you're not sure about, but the fact that you stopped there tells the reader that that's where the uncertainty is. And so if we had drawing another scale here. Close to the same size. And let's say we had this is still 1 meter and 2 meters, but we didn't have any markings in between. And let's say we have the same object. How do we measure that? Where is the uncertainty now?
After the 1?
After the 1, right? We wouldn't go to the hundredths place, because if we don't have decimal markings here, then we're not all going to agree on the tenths place. So we're not going to report to the hundredths. So with this in mind, we look at this. Some people might say 1.5, some might say 1.6, some might say 1.7. All of a sudden, by changing the ruler, we change where the uncertainty is. Which seems weird, right? It seems like it's the same object. It seems like the uncertainty should be the same no matter how you measure it. But that's not how it works. The tool that you are measuring with affects how certain you are. Right? And so you always go 1 past the smallest decimal markings. If I do that, is it a decimal scale now? If we say that this says 1 1/2.
Not fractional scale.
I gave it away when I did that. But even if I write it like that, though.
Why not?
Do we have 10 equal markings on there that we can agree on?
No.
No, so the fact that it has a marking at 1.5, that's there to help you guess the tenths place. But that doesn't mean you get to go to the hundredths place. Because is it 1.5 or 1.6? That's going to depend on who you ask, right? Even with this line to help you measure, we still have the uncertainty in the tenths place. Right? So it becomes important to be able to look at these scales and say, that's my smallest decimal scale. And say if I did the same thing here. If I added all these in there. It looks more accurate now, right?
Yes.
We should be able to go to another decimal place, right? No. It still only has decimal markings for the tenths place. It doesn't have decimal markings for the hundredths place. It has a little helper. It has a fractional scale for the hundredths place. But fractional scales, we don't know what to do with because they don't behave like decimals. So if something is fractional, and if you have a marking there, you can use it to help you guess. Like all of a sudden, that makes pretty clear it's definitely under 1.55. So maybe 1.54 is looking even better. We might agree all together 1.54 starts looking a lot more reasonable. That doesn't mean we get to go to 1.545. And because we definitely are not certain about the 1.54. Right? If I was really good and you guys had binoculars, now all of a sudden it's a decimal scale at the hundredths of a meter. Now we can estimate the thousands. And if you zoomed in, if you're up here right next to me, you can look and say, oh, it's definitely between 3 and 4. So it's 1.53 something. Now all of a sudden we estimate the thousands place. The more accurate the measuring tool, the more digits we're going to put on. And you're always limited by where's the smallest decimal scale. Right? And so there's a really hard, it's a hard line when it comes to this is the rule for it. But it always comes back to you don't want to write numbers you're not certain of. Or rather, more accurately, you only want to write one number that you're not certain of. You guess the last digit, and then you leave it. So this is all well and good, as long as we're the ones measuring the numbers, somebody else is measuring the numbers, or if we want to do some math with these numbers, somebody else is measuring the numbers, you can assume that they follow the rules too. Usually, unless you get a number that really, if somebody went to measure this, and I didn't look at it, and they wrote down 1.532712. I'm gonna look at that and that's not reasonable. It's not, you didn't really measure it down to the micron.
You didn't eyeball it.
Right, you didn't eyeball it with this ruler, with any ruler really. Right, so unless you get a number like this, you can assume that whoever wrote the number down followed these rules. The problem is if we want to do any math with it, a lot of times when we multiply decimals, we get really small decimals, right? We need to know where to round so that we can indicate where the uncertainty is. So it's not just about knowing how to measure so that we can find the uncertainty. We also have to be able to round on our calculator so that we know where the uncertainty is. And so we can indicate to somebody else where the uncertainty is. So we can do some more practice with these just for the sake of trying this out. Not that this really matters, but let's say that it's 7 and 8 meters. You had that marking there, and what would we measure that as?
Definitely over 7 meters.
Definitely over 7 meters, right? So we know we can do that. We're going to estimate to the 10th place, right? So it doesn't matter what the object is when it comes to writing down decimals. It matters what the measuring tool is. I know I've said that once already, but I'm just reiterating. Every time we use this ruler to measure something, you're going to go to the 10th place. Every time you use that ruler, you're going to go to the 100th place. So, and then we can look at this and say, well, and you can even use your, make an imaginary fractional scale, like, well, that's 7.25, 7 1/4. It's less than that, definitely, so maybe you call it 7.1 based on that. Somebody else might look at it and say 7.2.
Wouldn't you only be able to guess that if that center line is marked? Because if that's just a regular mark, are we supposed to assume that that's halfway, or because it's not marked, we don't?
It's not marked. It's like I said. So when you have something there, it's not a decimal scale. It's there to help you guess that last digit. Okay. So even if it's not there or not labeled as that 7 1/2, you can still look at it and say, well, there's only one mark between these two. It's probably halfway or close to halfway.
Okay.
But even without that, we can look at this and say, well, it's definitely not 7.3. Maybe 7.2, maybe 7.1. And that's why we have some uncertainty associated with it, right? Because everybody's going to estimate that differently. To me, it looks more like 7.1 than 7.2, but, you're not wrong if you wrote 7.2 because I know my number and your number are both plus or minus 1. To me, those are the same measurement, more or less. Right? Because we're only off by 1 in the last recorded digit. That tells me that they're really close to the same number as far as using this to measure. And let's say, we'll just leave it at, I'll do 2 and 3, why not? Still really the same thing, but we still know we're going to be going to the hundredths place, no matter what, right? So let's say we measured it and it was, I left all my little helper lines on there. These are the big ones. So 2.1, 2.2, 2.3, close to 2.3, 2.31 maybe? Somebody might disagree, say 2.32. Again, same number, doesn't make a difference as far as you're not wrong because you say 2.32. We're using the same measuring tool, we're reporting the same number, and it's close on that last digit. What do we do if it looks like that?
2.25 something?
So that's 2.1, 2.2, 2.3.
Oh, okay.
So what would we write? It's not two, you might look at it and say 2.31. It looks like it's right on the line, right? At least that's what I was trying to draw.
It's still uncertainty.
There's still uncertainty.
There's still uncertainty, exactly. So we're going to leave, we have to write to 0, even though that's not going to affect any math that we do. You guys all know that adding zeros on the end of a decimal doesn't change the number, right? But it does change where the uncertainty is. If you write 2.3, that means plus or minus a tenth of a meter. If you write 2.30, that's plus or minus a centimeter.
Yeah.
You could write 2.29, and that still will put the uncertainty in the same spot. And that's one way to get around the fact that, it feels weird to write the extra 0. In the sciences, though, if something ends in a 0, that 0 is written because it was measured. It's written to tell you that's where the uncertainty is. And you can write the uncertainty, sometimes you see it written explicitly. See it written plus or minus, plus slash minus. It's just a lot of extra writing. You have to do that every time you make a measurement, right? And then up here, go ahead.
Oh, sorry, I didn't see through your arm. I thought you just put plus or minus 0, and I was like, what?
No, yeah, so anytime you're not sure, or you want to make it really explicitly clear that whoever reads this knows where the uncertainty is, you can do this. It's implied, though, if you're writing your digits correctly. If you write your measurements correctly, you're supposed to assume it's plus or minus 1 in the last place that you wrote, the last digit that you wrote. Right, which means this one could be 2.29, so really technically 2 of the numbers would be changing in that case, but you guys can all see how that's really the same thing, right? It could be off by 1 here, which doesn't really change, when I say we're certain about the tenths place, technically the tenths place in this could be it could be a 2 right here, but we're still certain, we're not off by an entire tenth, is what I'm trying to say.
That's where rounding up comes in.
That's where rounding up would come in. All right, and there are other things too. This is where I would normally have slides that have some other things that measure. A protractor has uncertainty associated with it. Okay, I'm going to not erase that one since I took such good care to make a beautiful decimal scale there. If you have a protractor, degrees for way off. This is less than ideal. But it kind of works. You can kind of get the picture that if you're measuring the angle of something, and you only had markings for every 10 degrees, you're going to estimate to 1 degree. You have markings for the 10, so we can definitely do this and say it's definitely between 50 degrees and 60 degrees. Like, we could say that if my drawing was better. If I got out the actual protractor. But everybody could agree that it's 50-something degrees, and then we'd be estimating the ones place. Most protractors actually have markings for the individual degrees, right? So it would be, there's 55, 1, 2, 3. Well, let me push it then. 1, 2, 3, 4. And if that was accurate, then you could actually zoom in, with your binoculars and see. Now all of a sudden we'd be estimating the tenths place. Right? Measuring liquids, similar thing. You're looking for the smallest decimal scale. It's a little bit trickier with liquids. I'm going to try to take my time and draw this well so you can see what's happening here. This is the graduated cylinder. We have some liquid in there. And we have markings for, let's see, this is 10 milliliters. This is 20 milliliters. If we don't have any smaller markings, how would we measure this? What would you estimate?
10 would be the automatic.
Definitely more than 10.
Right. Also the 1 as well.
13.
13, yeah. Somewhere in there. 12, 13. Anybody know how to measure a liquid? The meniscus.
Great.
Yeah. And when you're dealing with water, and your container is glass, you're measuring the bottom of the meniscus. Turns out that different liquids and different containers will interact a little bit differently. Like if you have mercury, the meniscus is reversed. So it goes upward instead of downward. Because mercury sticks to itself better than it sticks to glass. So in that case, it would look something like that. Looks really weird when you actually see mercury in glass like that.
Did you measure from the bottom or around?
You measure from the flattest part of the meniscus. Which means when it's water, you measure from the bottom, and if it's mercury, you measure from the top. Just random things. You probably will never need to actually measure mercury in a graduated cylinder, but now you know. Yeah, so we estimate this 13, 12. If picking your glassware becomes important here because some glassware only has markings for every 100 milliliters, and some glassware has markings for a tenth of a milliliter. And then you'd be able to estimate to the hundredths place. So picking your glassware actually depends on how accurate you need your number to be. So if we did add one more here, see there, 1, 2, 3, 4. Close. Now all of a sudden, starts looking, maybe it's more like 12.0. Again, based on my bad scale, but assuming these were trustworthy. Right? So we will practice this in lab next week. Your first lab is going to be a lot of take a ruler, go measure something, make sure you get the right number of decimal places. Here's a graduated cylinder, measure some water. Tell me how much you have with the right number of decimal places. Again, super riveting stuff. We're laying groundwork so that you can trust your numbers down the road. All right. Let's use this scale over here, and we're going to zoom out a little bit. Let's say that this is 1,000 meters. And this is 2,000 years. How long is the object? The numbers didn't really change, right? But the way we're going to write them changed. So 1,000, 1,100, 1,200, 1,300. So 1,300-ish. Where's the uncertainty?
The tens.
Yeah, we estimated the tens place. It looks like it's a 1,300 plus or minus 10. We could write that. That tells the reader that, hey, we did measure this spot, we didn't measure that one. Or we use scientific notation. If we use scientific notation, we can control exactly how many decimals we need to write and exactly where the uncertainty is. So if we write 1.30 times 10 to the 3 meters, we can write that 0 as a decimal. And that tells you that it counts, that we measured it. If you just write it like this, especially, it's really common for people to measure a number, write it like this. Now, I have no idea where the uncertainty is. Is it plus or minus 100? Plus or minus 10? Plus or minus 1? If this is how it's written, this is what we call an ambiguous number. Ambiguous just means undefined. We don't know where the uncertainty is here, so we have to assume it's only that it's plus or minus 100. When really, we actually went to the trouble to measure that tens place, so we actually have to throw away some of our knowledge when somebody goes to read this, if we don't take the care to write it properly. Right, so this is one of the reasons why scientific notation becomes important, because if you measure something and if you get an ambiguous number, you need to write it like this. And this is where, who was it earlier that said, well, why don't we just say it's 29 instead of writing 3.0, right? That's still an ambiguous number though, right? Because now we can look at this and say, well, we know that the 9 was measured, but what about the 1s?
Wouldn't that be more accurate in scientific notation though? 1.29 times 10 to the third?
No.
No.
So mathematically, they're just as uncertain. It just, adding that 0 is not going to change your calculation when you plug it into the calculator, but it does as far as how many digits you get to keep after your calculation.
Still plus or minus 1.
It's still plus or minus 1 in that last spot, regardless of whether we write it down this way. In lab, the reason I bring this up is in lab, it's going to be tempting sometimes, rather than have to rewrite something in scientific notation, it's tempting to just say, well, maybe it's just under that, so that I can write 9 instead of 0, and not have to do scientific notation. I get that, but at the same time, it's even better to just get good at scientific notation. Because it's not going away, especially if you study anything big or anything small. Because you're going to need to do calculations at some point where you take into account that you're dealing with something that's extremely big or extremely small. And it means you're going to use scientific notation.
So if you're working with numbers that are given to you like this, that are uncertain, would you give your answer in the same decimal place, or?
So we'll talk about that in just a second. So when we're talking about where the uncertainty is, it's pretty straightforward when we're looking at measuring the number for us to be able to say, oh, obviously plus or minus 10 based on the measurement. If you're sometimes, though, if we're doing linear multiplication or division, we don't necessarily care where the uncertainty is. We care how many digits were measured. So these are what we call significant digits. Any digit that you actually measured is a significant digit. Or we call significant figures, which gets abbreviated to Sig Figs. And if you've had a chemistry in high school or something before, that's probably you're going to have flashbacks now. Sig Figs is, I'm going to mark you all down on Sig Figs, everyone. Nobody will get through this quarter without being marked down on Sig Figs at least once. Sig Figs are the reason I've never had a perfect test in this class. Because there's just so many places you can screw up with Sig Figs. And most of them don't really matter. Most of them, okay, maybe I underreported Sig Figs on my final answer, so somebody thinks my number's not as good as it actually was. But it's something we always need to be paying attention to because it tells us where the uncertainty is. Right, so when we're counting Sig Figs, we basically are counting what are the digits that we measured. So if we look at this number here, this has two numbers that were measured. The tens place is measured and the ones place is measured. We would say that that's 2 Sig Figs. And we'd say that the uncertainty is in the ones place. They're really two different ways of talking about the same thing. Talking about where the uncertainty is sort of a raw number that tells you exactly how far off you could be, which is useful. But looking at the number of Sig Figs tells you how good your number is in a different way. The more Sig Figs you had, the more carefully measured the number was. So more Sig Figs is also good. And usually more Sig Figs means less uncertainty, but it depends a little bit on what your measuring tool is and how big the object is, subtracting or multiplying. So 12.0, how many Sig Figs? 3 Sig Figs. And where's the uncertainty? Tens place. 54 degrees. 2 Sig Figs, plus or minus 1 degree. Right, so when this is all we're studying, it's easy enough to pay attention to it. It's all really simple stuff. When we start asking to do more math or be in a lab and be measuring 5 things at once, it's easy to forget these rules. That's why I'm taking time with really drilling it in today. Right, last digit is where the uncertainty is, and we're really, with the uncertainty, we're usually talking about a place, a decimal place, not, when I say digit, I don't mean that the 9 is where the uncertainty is necessarily. I'm saying that tens place, this digit in the number is where the uncertainty is. Okay?
Next question.
Yes?
So with the 1290 right there, the 9 is the last Sig Fig? Is that right?
So it is because we just measured it ourselves, but it is the way it's written, it's ambiguous.
Right.
It's why it's confusing, right?
Yeah.
Is it plus or minus 10 or is it plus or minus 1?
You wouldn't want the 0 on it.
We would want written, when you write it this way, it's really easy to see how many Sig Figs there are, right? That's an advantage. If it's written in the coefficient of scientific notation, it's a Sig Fig. You don't write it unless it's a measured number.
Just to clarify, like that is like mostly something that happens when you have numbers that are greater, or they don't have like a decimal, you're not going past the like 1 place.
Yes. So by changing our units, we could actually get around that, right? What's 1,000 meters? Kilometer. So if I just did this instead, we can measure the same object, write it as just 1.29 kilometers, and that's the same measurement. It's explicitly clear how many Sig Figs and where the uncertainty is. Right, so picking the right units can make a difference, but sometimes we don't get a choice. Sometimes in order to use a certain equation, we need it to be in meters, or we need the mass to be in kilograms, even though we measured it in grams and that's what works best. Right, so we still need to be aware of how scientific notation works, because sometimes we just don't have units small enough, or it's going to be more work to get it to those other units than it is to just write it in scientific notation. All right, if I say, I was watching Giants game last night. Well, it was actually 2 nights ago that the game was on, but I'm in the Black House, so I always stay 1 day behind usually. So Monday night's game, Tuesday's game against the Padres, first game against the Padres. And one of their pitchers was throwing 101 miles per hour. How many Sig Figs, where's the uncertainty?
Three Sig Figs.
3 Sig Figs. It seems like it's cheating, right? They're measuring this, they're throwing it up there, and like, oh, 101 is a big difference than 102, but really it's all included in the uncertainty, right? It could have been a 102-mile-an-hour pitch that registered as 101 for some reason. Somebody moved the speedometer when the pitch was being thrown. I could throw it off by that much. Right, so if they really want accurate numbers, they actually have ways to go even more. Anybody know what the fastest fastball ever clocked was? 105.1 for all this chapter. And they actually had the 10th place registered for that one. Everybody was pretty sure he was going to break the record, so they brought in somebody who could get more accurate. What was your question? But obviously that makes a difference, right? You look at this number and you can look, wow, they really measured that well compared to this number. At least it seems like that. It also makes it really easy to over-report your certainty when you're doing math with something. You just round in the wrong spot, and all of a sudden your number is worthless because everybody thinks it's better than it is. Incidentally, that's probably not the actual fastest fastball. Nolan Ryan probably is the fastest fastball, but they changed how they clocked fastballs, and they used to measure it like that when it got to the plate, as opposed to when it left the pitcher's hands. And if you work the math backwards and the physics backwards, Nolan Ryan probably had that thing. But that's neither here nor there. Let's get it even better. 343.29 meters per second. How many Sig Figs? 5. Where's the uncertainty?
900.
The hundredths place, or you can say the 9, but just remember that you're talking about that decimal place. That's the speed of sound at sea level at perfect atmospheric pressure. All right. So the one thing I want to go over before we take a break is now what we do with these rules when we have to do the math. So if we're adding and subtracting numbers, what happens to the uncertainty?
It increases.
It increases.
We're uncertain where it is.
We're uncertain where the uncertainty is. Yeah. It changes. Let's say I'm going to drive. I know that it's 5.3 miles driving to my house. And then I'm going to drive to Sacramento, which is, 97 miles. If I want to add the 97 miles, which is plus or minus a mile, and the distance to my house, which is plus or minus a tenth of a mile, how far off could I be with my answer?
1.3.
1.3?
1.1.
1?
We just generally say 1. We keep it to be plus or minus 1 in that last digit. So when we add these together, when you plug it into your calculator, you get, what, 102.3? But if I could be off by a mile here, and only off by a tenth of a mile there, this is really controlling the uncertainty, right? So we're going to round our answer such that it reflects that it could be plus or minus 1. So we would cut that off and say it's 102 miles. There's no point including this if I could be off by a whole mile here. Same way if your friend is driving up from the Bay Area and they're going to be here in an hour, and they say, let's say they said they're going to be here in an hour, and we all know that's probably plus or minus 10 minutes, right? If your friend called you to say, oh man, I got stuck at that traffic light in Placerville, I'm going to be 15 seconds late. That's absurd, right? You already have so much more uncertainty that little bit, even though he might have gotten out a stopwatch and measured how long he was at that stoplight, Doesn't matter, because the uncertainty was already larger. Doesn't matter that he stopped for 15 seconds plus or minus a second, when he was already plus or minus 10 minutes. Right? The largest uncertainty controls your answer, controls how many digits you get to keep. So if we're measuring physical objects, usually we're going to be using the same ruler for both of them, so it's not going to be that big of a deal. But if we're measuring something like a football field plus the length of, your shoe, you can measure the length of your shoe with a ruler, and then have to use, a pedometer or something to measure how long the football field was. The largest uncertainty is going to dictate what you write down. And same for subtraction too. So according to PEMDAS, really, when we have PEMDAS, please excuse my dear Aunt Sally. I'm sure there's other ways of remembering it too. That's one that I always remember. Order of operations. It says addition and subtraction separately, but really they're the same step. Addition is really just adding a negative number, right? So for addition and subtraction, they're going to have the same rule. You keep the same, the largest uncertainty dictates the decimals that you write down.
Does it matter when you have to convert it?
It does, because conversions are multiplication and division.
Right.
And so all of a sudden that changes things.
So then which uncertainty do you go off of? If that problem was 5.3 miles and however many kilometers, which one do you go for and why?
So in order to add them, they have to be the same unit. So we have to do the conversion first.
Okay.
So but let's talk about, if we're just trying to, I don't know, let's say that the Caldor fire was on average 5.3 miles wide and say 52 miles long. If we're multiplying this and get the total area, we're not going to keep the uncertainty in the ones place. Because when you multiply things, things can get really big or really small in a way that our rules for just keeping this uncertainty in the same digit doesn't work. So for multiplication and division, you keep the same number of Sig Figs. So addition, subtraction, you keep the same uncertainty. Multiplication, division, you keep the same number of Sig Figs. So for this, I can't do that one in my head. It's going to be like 256 or so. Something like that. 220, yeah. Wait.
Let me go.
275.6.
275.6. So that's what we get when we plug it in. Our units get squared because we multiplied them. We only get to keep 2 Sig Figs though. The area got much bigger, but we can't keep our uncertainty all the way down to the ones place. Because if this one could be off by a whole 10, and this one could be off by a whole 1, you have to compound those when you multiply, and the uncertainties get compounded too. So we actually would wind up only keeping it to the tens place. So 280 plus or minus 10 miles squared, or 2.8 times 10 to the 2 miles squared. We round it up. So we're not just going to chop this off and ignore it, although that would still be within Sig Figs at the end. We want to round to the nearest value here, which would be round 5s up, and everything below 5 gets rounded down. And so, go ahead.
So the Sig Figs, okay, so you have 2 on each one, right?
We have 2 Sig Figs here, 2 Sig Figs there.
I remember you were saying addition and subtraction, you keep the same uncertainty, and then by the time I wrote that down, the multiplication and division part, I lost what you said.
So, yes, I will say it again. Keeping the same gets a little ambiguous too. So, with addition and subtraction, the largest uncertainty controls where you write your digits down. For multiplication and division, the smallest number of sig figs is your worst number, was the number that was measured the least accurately. So your smallest number of sig figs controls the sig figs that you write down at the end.
Smallest.
So if one of those had 3 sig figs, you'd still use 2.
I just make it a 0, so I can still use the same number. So if it's 52.0 and 5.3, 2 sig figs and 3 sig figs. Well, that one's going to control our uncertainty because the uncertainty is a larger percentage of this total number. You could be, our uncertainty is like 10% of this entire number, right? Versus being 1% of this number. So that means our answer, our uncertainty could be off by 10%, which means we're going to keep this only 2 sig figs when we multiply. It doesn't matter how accurately you measure this number if this number only has 2 sig figs.
So like 5.3 times, say, 25,786.
Does it make a difference how well you measure that
Your
one?
answer is going to be just 2 digits times 10.
Yeah, exactly. And so that's why both of the numbers wind up mattering. And you need both of your numbers to be accurate in order to be able to keep many sig figs in your answer. Right? And so it's both of these, when I explain, I'm standing up here and explaining it, and you're thinking about nothing but sig figs, these rules kind of make sense. You could probably even keep them straight right now. The second you have other things to be worrying about, other math to set up, a word problem you're trying to read through, remembering which sig fig rule goes with which goes out the window. It's the first thing you forget. I don't know why, but that's just always the way it is. It is for me too. All right, so the trickiest thing is going to be keeping those 2 rules straight. Knowing when do I keep the same uncertainty, when do I keep the same sig figs. The way I always remember it is the addition and subtraction is when the rule makes sense, and multiplication and division is when the rule is easier. It's easier to keep the same number of sig figs than it is to worry about where the uncertainty is, right? Once you get used to counting sig figs. But that's just the way my brain works. So, yeah, John.
For addition and subtraction, are you rounding to the largest decimal place of like the numbers that you were given initially?
You are rounding to the nearest. You're not always going to round up. You're going to round. So if we added these 2 numbers, 5.3 and 52.0. Or sorry, let's do 5.3 and 52. When you write it like that, it becomes really easy to see where the uncertainty is, right? And the fewest decimals is the one, that's where you're going to stop. You get, what, 57.3 when you plug it into your calculator. We're going to round to the ones place, and in this case, that means rounding down. So it would just be 57.
So like the largest decimal place is how it's going to read it.
Yes, the largest decimal place, where the largest uncertainty is, which means the number with the fewest decimals.
So if it was like 5.6, then we would just round the whole number to 58.
Right, if it was 5.6.
Okay. So you don't just drop off the number you rounded.
Exactly, don't just drop it, you round to the nearest for that particular digit.
Okay.
Right, so one of the reasons why you were taught how to round back in, I don't know, 5th grade, is that when you were around? Somewhere in there, 8th grade? I have no frame of reference for learning arithmetic anymore. It's been too long and my kids aren't old enough yet. All right, let's take a break. We're going to come back and we're going to practice this. And then we're going to actually use it in something that matters. All right, so let's come back at 5 after.
Actually, Sean, I have a question.
Because I'm trusting that you're not just making something up.
Okay.
And then.
And really, it's really, I'm not sure I said accurately measured. I may have, but it doesn't need to be there. Any digit is measured. And that includes the ones we know for sure and the ones,
Yes.
I guess.
That's why I assumed.
Yeah. Good question.
So I had a question about the labs.
Yeah.
How many labs are we have to meet?
So we'll meet twice a week, but it'll be one lab and one in-class assignment.
Okay,
This week they were kind of both in-class assignments. We didn't actually get any wet chemistry in.
okay, for sure.
But usually there'll be one lab in the chemistry lab where we're mixing stuff up or measuring stuff and whatnot. And then one that will be more of like the in-class assignment, like the math review.
Okay. And then so it's divided like Monday, Wednesday, and then Tuesday, Thursday,
It's-
that kind of.
So it changes a little bit because it depends on the order that we hit the material,
Okay.
when it makes sense to do that. So, but it's all in the syllabus. The syllabus has them labeled,
Yeah,
you
I
know,
saw that.
on, you know, this week it's Tuesday is the ICA and Thursday is the lab.
Okay.
And,
Yeah, I just didn't
and
know.
so
if it
even
was-
it's, I know it's hard for work schedules.
Gotcha. Yeah, I didn't know if it was like you either come in Tuesday or Thursday, or it's like if you're in the Monday, Wednesday class. But I get what you're saying. Though.
Yeah, so yeah, Monday, Wednesday, they meet with me Monday and on Wednesday. You meet with me on Tuesday and on Thursday. It's just, and we're only one of them is actually going to be an experiment usually though.
Okay, for sure.
Okay,
Thank you.
no problem. Any of you grew up with dial-up? I've dial-up internet, yeah. This is what I remember it feeling like. You click a button and you sit there and you wait and you hope it works and you hope you didn't click the wrong thing for the next minute and a half.
I remember clicking the wrong link on accident and then having to like fix it for like the next 10 minutes.
Yeah. It was a different world. Plus, nobody could call the house while you were on the internet, so you had like 10 minutes was all the time you had on there before somebody was going to call and you needed to get off. Yeah, in the dark ages.
We also able to have more patience with it because you didn't think something was wrong.
It's true.
Now you click it, you're like,
Yeah. Yeah, there was more faith that it was actually going to eventually get there. Because if it wasn't going to actually get there, you'd get that horrible disconnect noise and you'd have to listen to the modem sing the song of its people. All right, well, me going just off the board, it's not that bad so far. Don't forget, you can always go back and look at the slides later and see what I was getting at with some of these things. There's more practice. We'll just go back to where we were. All right. So let's just recap one more time. How do we know? So figuring out where the uncertainty is just a matter of looking at the number, right? And looking at the last digit that's reported. Counting Sig Figs, we do actually have specific rules for that because it's a little bit trickier. The first rule is the easiest. If it's non-zero, it's a Sig Fig. Easy enough, right? Everybody's able to look at a number and know if it's zero or not. I trust at this point. If it's between two non-zero numbers, it's a Sig Fig. So that seems like a silly thing to specify, but if I write 504.2, rule number one just applies to these. But if I measure the hundredths place and I measure the ones place, that means by definition I had to measure the tens too, right? You can't get this number measured without also measuring that zero there. That's what rule 2 is about. If it's a zero, but it's between two other measured numbers, it's a Sig Fig. If it's a trailing zero after the decimal point, so that's the one we did an example of already, right? Where we said 1.30. That's what I mean by trailing zero. So it's not any zero that's after the decimal point, but if it's a zero, if it's after a measured number, then it's a measured number, then it's significant fig. Right? So that's measured, and so are both of those, or I wouldn't write it. And so it doesn't mean. So how many Sig Figs are here?
4.
4. How about here?
2.
Just the 2. These are leading zeros. We're always talking about trailing and leading. I mean, relative to the first non-zero number, relative to the first number that I know is significant. So if it's to the left of the first number that I know is significant, it doesn't count. If it's to the right of a number that I know is significant, then if it's after the decimal place, it definitely counts. If it's before the decimal place, then I don't know, and it's ambiguous. And if I wrote 3,200, those are trailing zeros. They're after the last measured number, or the last sig fig that's non-zero. But I don't know if those are just there to tell me where to put the decimal point, or if they're there because I measured them. So that's, again, why scientific notation matters in this case. All right, so I will do my best never to give you ambiguous numbers, unless I'm specifically testing you on how many sig figs are there. If I say how many sig figs are there, then this is what I give you to answer. The right answer is, I don't know, it's ambiguous. Right, so don't be afraid. That's like option E on multiple choice test, right? None of the above. Those are always the hardest one to answer because did I do it wrong or is it actually E, right? E might be an ambiguous number. I try not to do that usually in real word problems and in examples, but if I'm testing you on how many sig figs are there, I might throw one of these in there and you have to say, I don't know, could be 2, could be 3, could be 4. Yeah?
At least 2?
It's at least 2, yes. If you ever actually got a number like this and you needed to do some math with it, you can't assume that these are significant. You know that that one is. So you have to assume that it's plus or minus 100, even though it might be better than that. So you wind up, if you're not careful, you wind up losing sig figs just because you weren't careful about how you wrote them down. Yeah.
And the number above the 20 there, you know it's two significant numbers, so you broke it down and said it's not ambiguous numbers?
It's not ambiguous because these don't count.
Why don't they count?
Because anything that's to the left that's to the left of the first non-zero number, you could put it in the scientific notation and you wouldn't write that 0. The other thing, the way I think about it is I can keep writing zeros here. That doesn't mean I measured them.
Sig figs are based off of scientific notation, right?
That is the foolproof way to do it. The rule number 4 here is just if it's in scientific notation, if it's in the coefficient, meaning that the decimal in front of the power, which at the end, it's a sig fig. So for all of these, I could write 3.200 times 10 to the, let's say I'm looking at this one here. If I write 3.200 times 10 to the 3, let's say we're talking about meters, just so I can put units on this. Now all of a sudden, it's explicitly clear where the uncertainty is and how many sig figs I have.
But from 3,200 in the scientific notation, you have to make clear that it's plus or minus 100, right?
Right, so if I was writing this number down, if we actually measured this and it was plus or minus 100, you might write it like this for a second while you're converting it to scientific notation. But when you actually write down the number, you want to make sure that when you come back to your notes later, you know where the sig figs were. Right, so you would either write it down like that, or if it was plus or minus 100, you write 3.2 times 10 to the 3. Right, so the same number mathematically, you enter it into your calculator the same way, and you would get the same answer either way. But this is going to control how many digits you get to keep after you're done doing your math.
So that's 2 sig figs, and that's 4.
And that's 4. Right.
So all you need to do to make that for certain before sig fig, you just put a decimal on the end of it, right?
So that is not an official way to do that. It's a common enough shorthand. I will show you that as well. So if you have a number that ends in 0, but it's plus or minus 1 in the ones place. So if I did this, That's 5 sig figs now, right? All of a sudden, that means that these two have to count as well. If I don't, then the uncertainty would be in the tenths place. If the uncertainty is in the ones place, you can do that. Write the decimal without writing anything after it. Is a shorthand way of telling a reader, hey, the ones place is where the uncertainty is. There's no way of doing that for the tens place, though, or anything higher than that. So it's sort of an informal way of doing it, but you wind up with the uncertainty in the ones place commonly enough that sometimes it's worth it for you to have at least seen that. If that is a way, that means this is a sig fig. All right. I promise we'd actually do some math with this and practice this. Let's see. Let's say we have a box. And that box has the following measurements. Say it's 12.10 centimeters long. .58 centimeters wide. And is it 3.12 centimeters tall. So clearly not to scale, but let's not worry about that right now. What's important is, how do we know what the volume of the box is?
Multiply three of those together.
Sorry?
Multiply all three of those together.
Yeah, for a box, volume equation is really simple, right? Length times width times height. So then we can get a number out of our calculator. We get 550.42416. And when you multiply units, you treat them like a variable in math. So if you multiply centimeters times centimeters times centimeters, you get centimeters cubed. In fact, a lot of things about units, we treat them mathematically very similar to the way you treat a variable. If you're adding units, the units don't change. Just like if you have 12x plus 3x, you get 15x. If you have 12 meters plus 3 meters, you get 15 meters. So, if this is our volume when we plug it into our calculator, we're clearly not going to keep all of these. Right? Because that would be telling us that the uncertainty was plus or minus 0.00001. That's probably not accurate. So, because we multiply, we're going to keep the same number of sig figs as our least certain number here, or least our number with the fewest sig figs. So 4, 4, and 3. So that means we're only keeping 3 sig figs. 550.
With that, you put decimal point.
Exactly, or put it in scientific notation. Or I'm not going to mark you down if you explicitly write out. If you write out the uncertainty, you can always say plus or minus 1 cubic centimeter. Usually that's more work than just putting it in scientific notation, though.
But we have to keep, in scientific notation, we have to keep that 0 because we were certain.
Because that's where the uncertainty is in that ones place. And the 0 is in that ones place. So when you write it in scientific notation, you keep that 0. Right? And that way, anybody who looks at your number, even if they don't know what the box looked like, they don't need to know the measurements, they can say the volume is 5.50 times 10 to the 2 cubic centimeters, and they know exactly where the uncertainty is, and how many sig figs your number has. And same with this too, as long as you make sure that you write your units.
Well, I can add this.
And if we added those two numbers, for all three of them, we keep the same uncertainty, right? Where is the uncertainty for each of these?
Same spot.
They're all in the same spot. If we use the same ruler for all of them, usually that's going to be the case, right? Because usually if you're using the same ruler for all of them, you're measuring to the same decimal place every time. So in this case, we wind up with 3.12 plus 12.10 plus 14.58, whatever your calculator spits out. In this case, it's already only going to be to the hundredths place. So we would keep it to the hundredths place, so we would get like 27 something, no, 23 something. 26 and 3, yeah, something really close to 30.
Actually, I have a question. If, let's just say, after we I add it all up, let's just say the number was something, something, the decimal, and then it ended in a 0, do we still have to keep that 0 on, even if it's at the very end? Because of the whole uncertainty.
If we're trying to say, let's say that our number came out to be, let me just make up some numbers that'll work for this example.
Well, so this number right here works, for example, because the 208 is.
Yeah, there you go.
So that would be your certainty point.
So what do you get for the answer when you type this in? Is it exactly, is it 30.00? 29.80? So when you get this, when you plug it into your calculator, right?
Right.
You actually have to go back and add the 0. Your calculator removes the 0 for you because it doesn't need to be there. But if we want to say that the uncertainty is in the hundredths place, we have to go back and add that. Yeah?
What's the best way to write a simple number like 10 or 20 for the uncertainties in the ones place? It seems weird to put that in scientific notation.
So you can put it in scientific notation, or you do that if the uncertainty is in the ones place. This is a really common way to do it as well. Is to put that decimal point there. So if I want to say 10 plus or minus 1, I can do that. It's not officially the correct way to do it. Officially, the correct way to do it would be to put it in scientific notation. Like you said, it looks dumb. Putting 10 plus or minus would be 1.0 times 10 to the 1. This is a common enough way of doing it that you should be aware of it. I'm not going to mark you wrong if you wrote it like this.
Okay. But you will mark us wrong if we don't put the decimal behind the 10.
I will mark you wrong if you don't put the decimal behind the 10. And like I said, by far and away, by at least an order of magnitude, probably more like 100 times, the most common thing I will correct you on is going to be Sig Figs. Not because they matter the most, but because they're the easiest to screw up. You will screw up Sig Figs, and it doesn't mean you don't get the material. It means that you weren't paying attention to one thing, or you switched these two rules up in your head, or something like that. At this point, I know that that's the way this class goes. Everybody messes up Sig Figs, and that's fine. In the real world, everybody messes up Sig Figs. The important thing is that you're always trying, and you don't give me an answer like this. Right? Normally, I would take off, out of a 10-point question, I would take off half a point for a Sig Fig error. If you did everything right, except you messed up your Sig Figs on a 10-point problem, I'll take off half a point. If you give me this, that's a whole point. And because you're telling me you are really sure about this number, way more than is appropriate. Right? So in general, keep it close. Pay attention the best you can, but don't sweat it if you do get marked down on Sig Figs. That's just how this class goes. Right? Until it becomes second nature, you will mess it up. And sometimes even then. In full transparency, I always just guessed when I was a student. I got marked down on Sig Figs a lot. I never actually learned the proper way to do it and why it makes sense until the first time I had to teach it. So that could be one of the reasons why I harp on it now. It's because I never learned it and now I get it. And now I won't say I think it's cool because it's still just Sig Figs, but I understand why it's important more than I used to. All right, we have a couple examples here. Let's say we're running the the Olympic 100-meter dash, and it's 100.00 meters. Anybody know who won the gold medals here, what the time was? Anybody follow track and field? I don't, but I know we just had the Olympic stuff, that's something in mind. Let's say that the winner ran it in 9.72 seconds. If we want to know their speed in meters per second, we take the distance, divide by the time, right? What is their speed going to be? I offset them for some reason, but this is a fraction. Units just wind up combining, just like with variables. If you had x over y, you can't do anything with it, right? So you just leave it as x over y. If you have meters over seconds, you can't do anything with it, so it's meters over seconds. What do we do with our decimals?
Round to the nearest 10. No, wait.
How many sig figs are we keeping?
3, so 3 meters.
Three.
10.
So yeah, 10. We're going to round right here. 10.3 meters per second.
Would we keep it like that, or do we have to do the scientific notation? Or does it matter?
So for this one, it doesn't matter.
Okay.
You could put it in scientific notation, but the fact that we're writing a decimal tells us already that it's 3 sig figs. Anybody who reads this and knows the rules will say 3 sig figs. Let's see, what about if we had, let's do a more interesting one. All right, let's say a room. Let's talk about this room, actually. We'll make this one up on the fly. Make up some numbers, too. This room is, we're going to call it roughly square, or rectangular. And it's maybe, I don't know, 10 meters by 12 meters. Let's say, just so we have some sig figs, let's say 10.5 meters by 12.0 meters. Let's say that's my ocular pat down estimate. I'm not off by a whole meter. I might be off by 10 centimeters. Probably not really that good, but let's just pretend that these are our numbers that we measured. What's the area of the room?
126 meters squared.
126 meters squared. Do we need to do any rounding?
That is round.
That is rounded. Is that the right rounding?
Yes. Yes.
3 sig figs, 3 sig figs. Yes. Let's say we've got that godforsaken post in the middle of the room. And let's say that post is 0.7 meters by 0.7 meters. What is the area that that post takes up? 0.7 times 0.7.
So you have to round it out.
We round it up, 0.5. Right, because we only have one sig fig on each of these. What is the area of this room minus the area of the post?
125.
So 126 square meters minus 0.5 meters squared. Our calculator answer comes out to be 125.5. But with subtraction, we switch rules.
Right, so it's still 126. So you have to round it back up, right?
We have to round it back up.
That's
I didn't mean to do that when I picked those dimensions. But the main thing thing is that when you, even if you're doing a word problem that has both addition and subtraction and multiplication division, you are going to have to switch back and forth between these rules based on what operation you're doing. You can't do all the math at once in your calculator and just get the right answer. You have to stop here and round before you can do the subtraction, or you're not going to get the right answer. You might, but you have the potential to get it wrong. And so the fact that we have plus or minus a 10 and plus or minus 1 means our answer is going to be plus or minus 1. We round the nearest 1, we have 126 again. If, for the sake of doing this problem, let's do that. So now instead of, you're going to get 0.64, right? Now let's round to 0.6. It didn't change anything about how many sig figs we had up here. But now when we do this, and we still are trying to round to the ones place, but that just bumped it over the hump, so that now all of a sudden, we're going to report our answer as 125. Because we're going to round downward. And really, and that's a really good illustration of why we assume it's plus or minus 1 right here. Because we made a 10 centimeter difference here, and we're reporting that it made a 1 square meter difference. Because really, this last digit is plus or minus 1. We were already off by a square meter. We had the potential to be off by a square meter. So when we do this subtraction, rounding it right there tells us we still could be off by a tenth of a meter. Right? Because we're limited by some of these other measurements. Did I see a hand up? Yeah.
So if you were writing that as the answer on your homework, you could put a decimal after 55?
No.
So if it's non-zero, you don't have to. It's not wrong to do that. But if you're writing a 5 here, you're already assuming that it's plus or minus 1 there. If we got a number that was, we do that, that's specifically telling you that that was measured, that that's where the answer is. It's already explicitly clear here because the 5 wouldn't be there if that wasn't where the uncertainty was. But good question. And this is not wrong to put it. And you could put the decimal anytime your uncertainty is in the ones place. You could just be in the habit of always using that decimal point. You're not wrong. Yeah?
If you have a big, crazy, complicated thing, you're supposed to stop and round, and you can't like put it all in together.
You have to stop to round anytime you switch operations. So if you have a whole bunch of multiplication to do, you can do all your multiplication and round at the end.
Oh.
If you have a whole bunch of addition and subtraction to do, you can do it and then round at the end. But when you switch between the two, you have to have the right sig figs going into the next operation, or you have the potential for it to be wrong. Right? So anytime you have addition and subtraction mixed with multiplication division, it's always going to be your trickiest sig fig problems. So let's do another one. We'll do a temperature conversion. Anybody, I would ask this, but I won't ask you to out yourself as a super nerd. Anybody know the conversion equation for Fahrenheit to Celsius?
9/5 plus 32.
I didn't even have to worry about it, you did it yourself. So yeah, so temperature in Fahrenheit equals 9/5 temperature in Celsius plus 32. These are exact numbers, meaning that they have infinite sig figs. It's not about 32, it's 32.000 out to infinity. But the fact that we have multiplication and addition means that we've got to be careful. So if we do, what's a good one? We do 42.1 degrees Celsius. We want to know what it is in Fahrenheit. Well, if we've got the equation right here, we're just going to plug that in right there and do the math. So, but we're going to actually want to stop in between to round. So 9/5 times 42.1, what do we get?
75.78.
75.78. Perfect. I thought I heard the same thing. How many sig figs are we going to keep? 3. Those are infinite sig figs. They're exact numbers, so they're not going to affect anything. So we're only limited by these. So it's 75.8 plus 32. And how many sig figs are we going to keep here?
All of them.
All of them.
Yeah.
Why?
Addition.
Because we added an exact number. Remember, this 32 is 0.000 out to infinity, plus a number where the uncertainty was in the tens place. And we switched from multiplication to addition. That's why these are so tricky, is you have to stop. Switch rules in the middle. Because if you only keep 3 sig figs, you're selling yourself short. That was a better measurement initially. You don't want to only keep 3 sig figs when you get to keep 4. And you get to keep 4 because that adding took us over 100. We gained the sig fig, but we kept our uncertainty in the same spot when we added the 32.
So if I didn't round,
Mhm.
rounding before I switched over to addition, I still have the same answer. I'm sure that's not gonna happen very often.
So sometimes you will still get the same answer if you wait to round at the end, but you won't know where to round. If you want to get your sig figs right, you have to stop. And there's a potential for it to be off if you don't stop in the middle. Your numbers might at least look different, especially if we rounded by more than 0.02. You know, if this was 0.5 and we rounded all the way up, and then you kept it and you wound up being, you could be off by a degree at the end. Plus, you don't know where to round at the end, because how do you know how to combine both of these same two rules at the same time? It's as much of a pain as it sounds like. It's actually easier to stop in the middle, right when you realize, hey, I'm going to have to add, and I just did multiplication. You have to stop, round, keep your right number of sig figs, and then add. And again, these are the absolute trickiest ones for sig figs for as far as knowing where to go. Most of the time, pick one of your 2 rules, and you're just going to use that rule for the rest of the problem. Because when you have both of them at the same time, things get weird.
So the only reason, sorry, I'm just confused just with the answer. The only reason why we kept all of the sig figs after that addition was because the formula itself was in. So if, let's just say the formula was like 9/5, 42.1 plus 33, meaning that this wasn't the actual formula for the temperature, would we then round up to 108 degrees Fahrenheit?
So,
Or no?
yeah, so if these are not exact numbers,
Right.
that changes everything. If this 9/5 is really only 1 sig fig,
Okay.
then that means that when you do that multiplication, you have to round it to the nearest 10 here. And if this is really plus or minus 1, when you do the addition, you're going to have to round to plus or minus 1.
Okay.
So knowing what exact and what's not winds up being important too, and we'll get lots of practice with that. Turns out there are very few exact numbers. Most numbers are going to be measured numbers, unless they're a definition. This is the definition of Fahrenheit.
Right.
The definition, it turns out we actually have redefined an inch to make it so there's an exact conversion for inches to centimeters. Back before the 1980s, everybody used this conversion, but it wasn't exact. It was convenient and it was really close to the right answer. It was like 2.540021 or something like that. It was something really close to 2.54 centimeters, which is 1 inch. In the 80s, I think, they actually redefined an inch to be exactly 2.5 centimeters. So this actually has infinite sig figs now. Looks like it's only 3 sig figs, but because it's a definition, it's exact.
We
Right.
said we changed centimeters to match inches better.
Yes. No, we said we change inches to match centimeters better.
So any ruler
Inches
for
change.
you-
That makes more
Yeah,
sense.
any ruler before that change is off by just a little bit. All right. So this actually leads into our next topic. I know we only have 10 minutes, but this is when it starts getting useful. We start talking about converting units. Anytime we can say two things are equal to each other, even if they're in different units, we can do algebra with that all of a sudden, right? If we take this, if we divided both sides by 1 inch, that's going to cancel out over there, right? And we get 2.54 centimeters over 1 inch equals 1. Well, 1's a really nice number to do multiplication with, right? What happens when you multiply something by 1? It stays the same. Well, that technically means you could multiply by anything that was also equal to 1 and not change your original amount. Right, if I could multiply 12, let's say I've got 34 inches. If I multiply that by 1, I get 34 inches, right? If I multiply by something else that's equal to 1, I also don't change anything. So, for instance, this ratio. So I don't change anything, but it looks like I do. Because I wind up with inches on top of a fraction divided by inches on the bottom of a fraction, they cancel out, right?
Yes.
And all of a sudden I'm in new units. This is the basis for how you convert units of the same object without changing what that object is. You just multiply by 1. You just have to know what these are called equalities. Anytime you can say two things are equal to each other, that's an equality. So 12 inches equals 1 foot, that's an equality. And anytime you have one of these that doesn't have a plus something attached to it, those always throw things off. So let's pretend like we don't have any conversions like that, like temperature. Anytime you can say two things are equal to each other, you can rearrange it like this to be this ratio, which we call a conversion factor. So all a conversion factor is a fraction where the top is equal to the bottom. And so most of you probably already know how to convert, feet to inches or inches to feet or feet to miles, maybe even, depending on what you have rattling around in your brain. But if I asked you to show your work, it would get a little bit tricky, right? You all intuitively know, if I want to know 5 feet and I want it in inches, I multiply by 12. This is why we do that. And if you can do it for the easy examples where you already intuitively know, it'll help you when you don't know what to do. And so anytime you want to change units, you're going to start by trying to cancel out the units you started. So if I wanted to take 5, let's say it's 5.0 feet, and I wanted that in inches.
1 foot equals 12 inches, so you put 1 foot on the bottom. Right?
Bingo. So I know I want to get to inches, and I know that 12 inches equals 1 foot. I want to set it up so that feet cancels out feet. So I'm going to set it up so that 1 foot goes on bottom, and the thing that's equal to 1 foot goes on top.
So you essentially multiply by 1.
It's exactly what you're doing. But it doesn't look like 1 because the units cancel out, and you actually have to do some math. Well, arithmetic. So this is exactly why when you say, feet inches, you just multiply by 12. This is why. and allows you to make it multiple steps too, because you can multiply by 1 once, or you can multiply by 1 as many times as you want without changing the number, right? So if I took 5, let's say, so this is going to come out to be, what, 60 inches. How many sig figs? 2. Right? This is exact. It's not about 12 inches in a foot. Right? But that's a measured number. So that has 2 sig figs, our answer has 2 sig figs. Same over here. 34 inches, inches cancels inches. We're going to end up in centimeters. What do we get for a number for this one? Give me the calculator number.
86.36.
But it would just be 86. Right?
Just be 86. And again, this is exact. It is now. It didn't used to be exact.
Can you say 2.5? But they use 1 inch?
No, 2.54002 something is what it used to be, and now they redefined an inch so that it's exactly 2.54 centimeters. So this only has 2 sig figs. So our answer is only going to have 2 sig figs. And so, again, you probably could do a lot of these conversions intuitively. You know what to punch into the calculator for a lot of these. Showing your work becomes important, though, when I ask you to do a more complicated one, like say...
I was going to say, but I want to see that one in centimeters. So then we're going to multiply the 60 by 2.4.
Right, yeah, so we wanted to go 5.0 feet, and we wanted to convert that to centimeters. 5.0 feet. I know I've got a conversion for feet to inches, and I know I've got a conversion for inches to centimeters. So you can combine these two to be one conversion factor, or leave them as exact as they are and just say, write them twice. Or write it once with 2 conversion factors in a row. That's equal to 1. So is this. We want centimeters on top because we want feet to cancel out feet and we'll be left in inches. And then we want inches to cancel out inches and left in centimeters. Again, if I showed you these 2 things, you might be able to do it in your head or at least know what to punch in the calculator. But it's really, really easy to divide by 12 when you were supposed to multiply by 12 if you don't write it out. If you write it out, you won't do that unless you make the mistake of writing something really dumb like 12 feet equals 1 inch. Which I see things like that. All the time people write 100 meters equals 1 centimeter.
So the answer to that though is 152.4. What are we keeping?
152.4. We started with 2 significant figures. That's exact and that's exact. So we're going to end with 2 significant figures.
Yes.
For 150.
So 1.5 times 2.
Or it's 150 plus or minus 10. Or 1.5 meters. If we went one step further, we could say 100 centimeters equals 1 meter. Right, so you can stack these however many times you want to get where you need to go. And so just knowing, let's add one more, well, technically 2 more. 5,280 feet is what?
1 mile.
1 mile. And let's add 1 meter equals 100 centimeters. These are all exact. A mile is defined as exactly 5,280 feet. A meter's, well actually, a centimeter is defined as exactly 100 centimeters is 1 meter. If let's take my randomly guessed estimate for how far it is to my house. I think I said 5.3 miles. If I want to know how many, sorry, meters, I didn't put kilometers out there. If I want to know how many meters that is, we have everything we need right there. It's just have to take it in a couple steps. But most of you probably have these, if not, you might not have this one memorized yet, but you will. Most of you probably have the rest of these memorized, even if it takes you a little bit to get to that one. You might not use that one every day. If we want to get to meters using the tools we have over there, we're going to start by canceling out miles. So we only have one conversion for miles, right?
280.
We could stop there and hit equals and get a number for it, or we could just keep going. And remember, I haven't been actually working through how you plug this into the calculator. I've been letting everybody plug it in yourselves. When you multiply fractions, you just multiply straight across. You multiply straight across on the bottom and do your division at the end. Or you could type this into your calculator as 5.3 times 5,280 times 12 times 2.54 divided by 100. Anything at the bottom, you divide by it. Anything that's on the top, you multiply by it.
So we only keep two significant figures.
And we still only going to keep two significant figures.
8.5 times 10 to the power of 3.
8.5 times 10 to the power of 3.
Oh wait, yeah, there.
Which, 8,000, is that a reasonable number for 5 miles? 8,000 meters?
Yes.
If I then take, it's hard to know in your head because you don't have firmware to process what 1,000 meters looks like other than turn it into kilometers, right? So 5 miles is about 8.5 kilometers. Yeah, that sounds about right. So at least the right ballpark. We didn't do something like divide by 12 when we were supposed to multiply by 12 anyway, where we'd be off by a factor of 100. And so, I don't expect you to be able to do this on the fly yet, the way as fast as we just did it right now. Your rules are always, whatever your first conversion is, it's supposed to cancel out what you started with. Right? And it's nothing wrong with stopping every step. Convert miles to feet, get an answer. Convert feet to inches, get an answer. Convert inches to significantly, off a little bit from here. It might come out to be 8.6 or 8.7 even, if you stop to round every step. But, all right, we're going to end there. We're going to get lots of practice with this. Whole next lecture is going to be conversions. Easy ones, and then tricky ones, and then fun ones, like using a speed to convert a time into a distance. Gets fancy.